Agora, os nossos próximos palestrantes, que são os caras que vão falar em inglês, que eu comentei aqui, cara, eles vão fazer uma coisa polêmica, porque eles vão falar de Webassembly, que é uma forma de ser, né, ele já me explicou ali, não é que eu sabia não, tá? Ele me explicou, de você rodar um código no browser que não seja JavaScript. E o que esse cara tá fazendo aqui? Olha, eu quero pedir encarecidamente para vocês não jogarem coisas só porque ele vai falar de uma coisa que não é JavaScript, que é para não ser JavaScript, tá bom? Então, eu quero pedir uma salva de palmas para a dupla Elia Maino e Willian Martins. E agora eles vão ter que explicar melhor essa história.
Hello, we can start.
Hello.
So, hello everybody. We can start by quickly introducing ourselves. I'm Elia Maino, a software developer, a junior software developer from Vicenza, a very small city close to Venice in Italy.
And I'm Willian, senior developer from São Paulo.
We both work in Berlin for Foodora, a food delivery company part of the Delivery Hero Group, which is actually the biggest food delivery company in the world. This is our front-end team. As you can see, it's really very great. We have a guy from Hong Kong, guy from France, India.
And we are hiring. If you want, you can talk to us after.
Nice. We can start. Today we will talk about JavaScript and WebAssembly. But what is WebAssembly? A simpler definition could be the following. WebAssembly is a new binary format to run compiled versions of program written in C, C++, and Rust with near-native performance on a browser. The cool aspect about WebAssembly is that it's not an alternative to JavaScript. It's made to work alongside it and to provide the developers the performance of compiled languages and the flexibility of JavaScript. In particular, with the JavaScript APIs, you will be able to include a WebAssembly module into your JavaScript one and to access all the functionality. So it looks really interesting, right? It is. But before dive deeper into it and explain how it works, we want to share with you how we started to work with it and why we are interested in it.
So, in 2015, I attended to BrazilJS conference, and the last talk, Brandon Ike, the creator of JavaScript, was speaking about the born, raised, and evolution of JavaScript. Who knows that one of the most infamous quotes of him was "always bet on JS." But at the end of that talk, he told something that got me stuck on my mind. Always bet on JavaScript and WASM. And that was my first contact with this name. But what is WebAssembly? What is the problem that this technology tries to solve? In that moment, I started my journey to answer those questions. In the beginning, I tried to go alone. But I didn't find enough motivation to start something so incipient. So I just forgot about it. Almost 2 years later, in 2017, I regained my curiosity about the team, but I had more questions than answered. So I decided to find someone who was experienced enough to join force in order to understand it. But it fails again. I heard things like, this won't thrive, this will never happen, or even, I don't care, this is something for 2 or 3 years. A couple of months later, I attended to JS Conf and I got in contact with this again. At that time, Mozilla set a Q&A session to answer developers' question about WebAssembly. So I took advantage of this chance and I threw all my doubts. And these sessions made me excited again about to research again about WebAssembly. Back to my quest to find a partner, I met Elia, a junior developer who just joined my squad. One day I was explaining here about my findings on WebAssembly, and I asked him to work together on it. And he accepted right away. So our journey just began. Partner found. What should we do to prove our concept?
So, to prove our concept, we decided to implement John Conway's Game of Life and to use it as a benchmark to measure WebAssembly performance. Probably most of you already know this game. It's quite famous. It is a 0-player game in which the world is a matrix, and each cell can be in two status, each dead or alive. And the only external input provided to the game is the initial state. The next state of each cell is determined by the number of his neighbors. For example, if a cell has less than 2 neighbors, the next iteration the cell will die. If an alive cell has exactly 2 or 3 neighbors, will stay alive. If it's alive and it has more than 3 neighbors, it will die. And in the end, if a dead cell has exactly 3 neighbors, it will become alive in the next iteration. It looked like a good example for our test, especially if we want to use a big matrix. So the plan was therefore the following: creating a big matrix and randomly filling it with 0 and 1 values, then passing this initial state to the renderer, render the state, and then ask for the next state to the environment. Repeating this last iteration in a loop. So, the structure of the project was written in plain JavaScript. And we decided to calculate the next state using 3 different approaches: VanillaJS, WebAssembly, and web workers. The time complexity of the next state calculation algorithm is the same for the 3 approaches. It's all of n times m complexity, in which n and m are the dimension of the matrix. Since the render part and all the other code that wraps the project is exactly the same for each implementation, we will not consider that in our measurements.
So we start the benchmark solution in plain JavaScript. Inside the main component, we keep splitting. Inside the main, on the JavaScript, we keep split the problem in smaller problems to try to trigger easily the just-in-time compiler improvements. So we'll talk more about the just-in-time optimization in a moment. So the results for this vanilla JavaScript was the average speed of the stage calculation varied from 9 to 4 milliseconds for a matrix of 800 columns per 450 lines. You may wonder why so many variations of these results, why so many functions to split this problem into small problems. We could do it on one for loop, but to answer these questions, we need to we need to show how JavaScript and just-in-time compilers works in order to make JavaScript to be fast today. The main logic behind just-in-time compilers is the way that it treats the same piece of code based on the metrics like the types and the frequency. In the beginning of the JavaScript, JS interprets the code line by line, make the startup phase faster, because the interpreter only needs to read the instruction, translate it, and run right away. The problem with this approach is when it needs to iterate over an array, for example. The interpreter has to translate the same piece of code over and over again. When this happens, the just-in-time compilers mark this piece of code as warm. When this piece of code is warm, the profiler sends this to baseline compiler that creates a stub for this piece of code and keep track of the line and the types that it calls. And so when this code is called with these types, just-in-time compiler only needs to use that compiled piece of code again. When this piece of warm code is called several times, the profiler marks it as hot. When the code is marked as hot, the just-in-time compiler sends it to optimize compiler. that makes an even faster version of this code. Make some assumptions based on the things like the types of the variables and the shape of the object. The problem is when these assumptions fails, just-in-time compiler needs to throw the optimized code away and returns to the baseline compiler or even the interpreted one. This phase is called the optimization or bailing out. When browsers compiling, when browsers keep trying to optimize and they optimize the same piece of code, the performance of this code can be even worse than the interpreted or the baseline version. So in general, browsers have a limit how many times they try to optimize it. So when this limit is reached, the browser will return to the interpreted one and run only the interpreted version. So to summarize, the phase of a code just-in-time compiler on a code on just-in-time compiler could be parse, compile, optimize, optimize, execute, and garbage collector.
Okay, so when we introduced WebAssembly before, we said that it was a big improvement for the web because of its performance. And now that Willian just explained how just-in-time compilers works, we can understand why. Here, we compare in a very simple way how the JS engine treats JavaScript code and WASM code. The just-in-time compilers optimize the code execution on the run. And all the overhead caused by this on-the-run optimization is caused by the unpredictable nature of JavaScript code. In fact, you can see in the picture that the execution phase of the JS is longer than it expected to be because of this. On the opposite side, WebAssembly is supposed to be faster and it's expected to perform better. Why? First of all, WASM is more compact, so it's faster to fetch. And in addition to that, WASM is a binary format, so it's way closer to the machine code than JavaScript. And so the phase of decoding, compiling, and optimizing are faster. And plus, we don't need to do as many analyses on the run as we do for the JavaScript, since all the optimizations are done at compile time only once. And in the end, there is no garbage collection if you compile C or C++, so you will save time even for that. In general, these aspects allow you to save a lot of time when you run the program. So WebAssembly sounds fast. We can see now how to use it. Currently, WebAssembly modules cannot run on their own on the browser. This is actually expected to change when ES module supports comes to the browser, and when this will be okay, you will be able to run WASM modules like ES modules. Just import type equals module, and it will work. But for the moment, you need to fetch a WASM file from your JavaScript, add some JavaScript glue, and run your WebAssembly program from JavaScript. Including a WASM file into a JS module is pretty easy, thanks to the official WebAssembly API. First of all, we have to fetch the module binary of our WebAssembly program and store it into an array buffer. Then we have to instantiate it using the function WebAssembly instantiate. And after that, we will have an instance of our WASM program from which we can access all the functionality exposed by it. Cool. So to include a WASM file, of course, we need one. And to generate a WASM file from a program written in C or C++ or Rust, we need a compiler. One of the most popular compilers at the moment, and the one we used in our experiment, is mscripten. It allows you to easily compile the code while providing automatically a JS interface to the WASM module. This JS interface comes with a lot of useful functions to deal with the WebAssembly, in particular with WebAssembly Memory. We will see in a while that it's a little bit tricky at the moment. The command displayed on the top right of the slide allows you to compile a simple C program into a wasm module, a binary file, and a JS module, which automatically wraps the wasm one. Having this output, we can easily import the JS module in our project and start using the functionality exposed. Mscripten even provides a very useful C library, which can be used directly into your C program. And a very good functionality of it is the one that allows you to export only a certain amount of functions using this keyword, mscripten keep alive. We used it, for example, to expose only the next state calculation function in our program and the initialization. All the rest is hidden when you compile your program. And this is very useful if you are a developer, you want to give your module to the public, release it, so you can keep private or the logic and expose only your interface. So what about Webassembly Memory? We mentioned it before. How can we access it? We wanted to reproduce the same logic of our vanilla JS in C. So we rewrote the environment component in C with this logic, with this idea in mind. Since the app is able to instantiate the game with an initial state, we needed to allow our JS code to write into Webassembly Memory. Mscripten came to help with 3 really useful functions to manage Webassembly Memory. The first of it is malloc, which allows you to allocate memory into WebAssembly and to retrieve a pointer to keep track of it. The second one is getValue. You need a pointer and the type that you want to read, and it allows you to read from JavaScript a value stored in the WebAssembly memory. In the end, we have setValue, which accepts a pointer, a value, and a type. And as you can clearly imagine, it allows you to write some values into the WebAssembly memory from JavaScript. Cool. So with these 3 functions, we were able to allocate in WebAssembly the memory needed for the arrays of the current state and the next state, and to set the initial state as current state when initializing our C program. The JS glue code was keeping track of the pointer to the next state array, and using getValue, we were able to read the next state from JavaScript at each iteration. Anyway, when we ran the project the first time, we noticed that the overhead caused by this continuously accessing and reading the memory from JS was a big overhead and was slowing down the performance a lot. So what we did was rewriting the C program, making only this memory access. 1 memory allocation on loading for the current state and next state, 1 memory write on loading, and the biggest one, 1 memory read on each iteration for the following complexity, O of n times m, the size of the matrix. So we measured the performance again after this rework, and the wasm implementation was still slower, surprisingly. Not incredibly slower, but still slightly slower, and this was like bothering us. We were expecting WebAssembly to be faster. So we struggled with this problem for a while. And a further test, a simple counter, made us realize that the overhead caused by the JS handover of WebAssembly can still be a blocker if the problem solved by WebAssembly is not big enough. To make this test, we used a simple compiled wasm file, and we fetched it with the WebAssembly APIs, so we removed all the possible overhead caused by the mscripten glue code. But as we can see, for example, in the Firefox measurement, the WebAssembly code is up to 100 times slower, a lot. This is because the just-in-time compiler doesn't know yet how to deal with wasm in the best way. Our hypothesis got confirmed in an article by Lynn Clark. She wrote, currently, calling a WebAssembly function in JS code is slower than it needs to be. the just-in-time compiler doesn't know how to deal directly with WebAssembly. So it has to route the WebAssembly to something that does. And this can be up to 100 times lower than it would be if the just-in-time compilers knew how to handle it directly. So you will notice this override if you're passing a single big task to WebAssembly module. But if you have to do a lot of back and forth between WebAssembly and JS, then the override is clearly noticeable. According to this, for the moment, the best way to take advantage of WASM performance is to delegate a big task to it and require them from JS from time to time, 1-2 times, not more. In our case, the next state calculation was triggered on every animation frame, and this was causing a way too big overhead, making the WASM implementation slower than the JS one.
After all, we decided to try another approach. We knew that could beat both of the previous approaches. We create a component which splits the initial input into small inputs and delegate in parallel programming using web workers. So to ensure that this will return everything on the correct order, regardless the order that each piece finished the computation, we create a promise for each web worker and resolve this by promise.all. In average, the speed of this stage calculation varied from 2 to 3 milliseconds for a matrix of the same size. The drawback of this approach is the memory cop to each work. Every time we call it, adding a small overhead. It could be solved by using a shareaway buffer, but this wasn't the subject of our research.
So, in conclusion, we have to say that WebAssembly might still look a little bit immature for the moment, but its future looks bright. Talking about browser support, the MVP of WebAssembly is already rolled out and shipped in the latest version of Firefox and Google Chrome. And there are plans to release it on Safari 11 and soon off Edge. In addition to that, there are more features planned to come on the next iteration of WebAssembly. In particular, the most interesting ones are thread support, garbage collection, direct DOM access, which at the moment is still not available, and ES6 module integration.
If you want to check out our code of our experiment, you can, it's open source on GitHub, you can fork it. Or if you would like to learn more about WASM, there is a lot of research on the internet about it. We filtered some in Portuguese here on this slide, and we plan to post some content about this in Portuguese and Italian as well. We shared the slides on that Twitter account, it's mine, after the presentation. So more important than this, this journey, more important than these results is the journey that we took that brought us here. We spent almost 3 months working something together, which not only made us learn about WASM, but allowed us to learn more about how just-in-time compiler works, how to profile and how to benchmark performance among different browser vendors. And in addition, we were able to remove some dust on our C code skills. I couldn't do it alone. I didn't find any support from my senior developers friends. I only could complete this journey together with a junior developer. And this brings us some important learnings about how juniors and seniors should work together. Do never underestimate a junior. We were a junior before, and we remember all the people that helped us to achieve the important milestones on our career. We should face the new technologies with the junior humbleness, and with our experience, help them to avoid the traps that we face on our way. Once I heard from a friend, Elia on origami philosophy about the learning cycle, which says, learn one, do one, teach one. We learned, we did, we taught. Our journey ends here. Thanks.
Thank you.
E aí, foi bom? Foi difícil? Foi fácil, né? Foi doce, né?
Foi nada.
Não foi doce?
Não.
Obrigado.